All right, welcome to The Explainer. Today, we are unraveling one of the absolute most fascinating puzzles in all of science, the microscopic building blocks of matter. You know, when you mix a few basic ingredients together and just watch them fizz and completely transform, it honestly feels a bit like magic. But actually, scratch that. It's pure mechanics. Let's investigate exactly what is happening at the very smallest invisible level when old substances seemingly vanish to create entirely new ones.
Okay, let's dive right into this. Imagine you're mixing baking soda and citric acid in water. If you've ever dropped a bath bomb in the tub, you know exactly what happens next, right? It immediately starts bubbling violently, producing a brand new gas. But here's the ultimate question for us today. Where did the particles that make up that new gas actually come from? I mean, they couldn't have just appeared out of nowhere. We started with solid powders and a liquid, and suddenly, boom, we have a gas escaping into the air. What is the microscopic origin story of those new gas particles?
To answer that, we have to look at the particle puzzle, visualizing the theories. The tricky thing about physical science is that we're dealing with a world so incredibly tiny that we can't just look at it with our own eyes to see what's going on. We have to create models. We need a way to literally visualize these abstract theories. Think about how you might use, say, colored paper circles or little physical blocks to represent different types of particles. If we assign one color to the citric acid particles, another to the baking soda, and a third to the water, how can we physically move those shapes around to show a gas being born?
And this brilliantly illustrates our puzzle. Looking at these actual models created by students who were trying to solve this exact mystery, on the left, you see the starting substances, the particles before mixing. Now, in the middle, they brainstormed what might be happening. Some thought, well, maybe the old particles just lumped together to make one giant new gas particle. But others had a completely different idea. What if they act like tiny puzzle pieces? What if the particles of the citric acid, or the baking soda, or the water actually break apart, and then those broken pieces snap back together in a totally new way to form the gas? So the crucial point is this, and this is exactly what we're trying to figure out today. When new substances form from old substances, the particles of the old substances might break apart and stick together to form entirely new combinations of particles. It's basically the universe's ultimate microscopic recycling program. We are literally taking apart old structures, unhooking those invisible puzzle pieces, and building entirely new architectural masterpieces at the atomic level. That is how a solid and a liquid can reorganize their parts to become a completely new, free-floating gas. Matter is just rearranged, it's never just created from nothing.
Moving on to looking to the past, Dalton's historical clues. Now, if you're finding this all a bit mind-bending, don't worry, you are in excellent company. Scientists have literally been trying to solve this particle mystery for centuries. To really wrap our heads around how we investigate this today, it's incredibly helpful to look back. Because long before we had slick, modern laboratories, pioneering chemists were observing gases forming and asking the exact same questions we're asking right now. Let's take a look at one of the giants of early chemistry, James Dalton, and the historical clues he left behind for us. Now, what's really fascinating about this are these early visual representations drawn by Dalton himself. The guy was completely obsessed with figuring out what air was made of. And by carefully comparing properties, he realized that air isn't just one single uniform blanket. It's actually a mixture made up of different types of gases, which he represented with these distinct symbolic drawings. He identified 4 different gases just by analyzing their unique properties. This tells us a lot. It tells us that if we want to figure out what a new substance is, we need to closely observe its unique properties, just like Dalton did. But how did Dalton and his peers actually test their theories about particles breaking apart and recombining? Well, they realized they needed to add energy to the substances to see if they could physically force new particles to form. And they took 2 very different approaches here. Dalton famously experimented by adding thermal energy. He heated and cooled substances to see what would happen to the particles. Meanwhile, some of his peers decided to take a slightly more electrifying route, literally. They ran electrical currents directly through substances, so you have 2 different types of energy, heat and electricity, both being used to try and rip particles apart. And they decided to test these energy methods on a substance we are all very familiar with, water. The results? Totally fascinating. When they heated the water, bubbles formed. And when they ran electricity through the water, bubbles formed there too. In both cases, adding energy to a single, simple substance caused a mysterious gas to be produced. This shared result is a massive clue for us. It sets up the perfect foundation for our own modern scientific investigation into how particles rearrange themselves. Let me ask you a question. Have you ever just stared at a pot of boiling water on the stove and wondered, What's actually inside a boiling bubble? We know it's a gas, for sure, but what kind of gas? And more importantly for our puzzle, is the gas created by heating the water the exact same substance as the gas created by zapping electricity through the water? Or did the different types of energy cause the water particles to break apart and combine in totally different ways? To answer this, we can't just guess. We need to step into the shoes of those historical scientists and run the experiments ourselves. Which brings us to energizing water safely, the investigation plan. Let's see how this historical context builds our very own actionable plan. We have a brand new line of investigation to pursue here. We need to see if new substances are formed when energy is added to a single substance, specifically water. We need to design an investigation that allows us to observe this phenomenon firsthand, capture the results, and analyze the data to prove our theories about particles rearranging. So, here is the game plan. Step 1, we're going to heat water to produce bubbles. Step 2, we're going to run electricity through water to produce a different set of bubbles. Step 3, and honestly, this is the ultimate challenge, we have to safely capture those gases from both of those reactions. Because think about it, if they just escape into the room, we can't study them. And finally, step 4, we test the properties of the captured gases. Because if the properties of the two gases are different, we know we've created two entirely different substances from the exact same starting material. Now, before we rush off to start boiling and electrifying things, we really need to address that giant caution warning. We are talking about mixing water, extreme heat, and electricity. Inherently, this is a highly hazardous combination. Heating water to extreme temperatures can cause serious burns, and I probably don't need to tell you that water and electricity are a naturally dangerous duo that can lead to severe shocks if not handled perfectly. Safety absolutely has to be the primary focus of this entire investigation. And this is exactly why strict scientific safety protocols exist. Testing these potentially explosive ideas is only possible and only valuable if it's done in a highly controlled laboratory environment. Our protocols include super safe guidelines. This means these experiments are strictly for an in-class, teacher-supervised environment only. For the electricity portion, we are absolutely not plugging anything into a wall. We'll be using very small, controlled amounts of electricity from a simple battery. I literally cannot emphasize this enough. Do not try to replicate these experiments at home. Science is about controlled discovery, not reckless risk. So, with our safety protocols locked in and our models predicting that particles will break apart and rearrange, we are left standing right on the edge of discovery. If splitting water particles with thermal or electrical energy produces a gas, what gas exactly will we capture in our testing tubes? Will we find oxygen, hydrogen, something completely unexpected? You now have the foundational knowledge of how matter recombines to form new substances. The only thing left to do is run the tests and let the properties reveal the truth. Keep questioning, keep observing, and I'll see you next time on The Explainer.